well, at 1:30. So that way, between me and the TAs, we'll have Monday, Tuesday, and Wednesday. There will be somebody available. So I'm planning to have this in 129 Bridge Annex. It's a little confusing because I have two offices, but this is my physics office. Okay, so last time we talked about the Boltzmann distribution. Which is appropriate for considering a situation in which there's a large reservoir and a system in thermal contact with the reservoir. The sense in which the reservoir is large is that it can gain or lose energy in its contact with the system without its temperature changing. The system then, in thermal contact with the reservoir, comes to temperature equilibrium with it. The temperature of system equals tau in the most probable configuration. We talked about the thermodynamic identity, which relates the change in the energy of a system to heat flow, tau times change in entropy, and work done. We also talked about free energy. We can think of the free energy as a function of temperature, as the value of U minus tau sigma when the energy of the system is chosen to attain the most probable configuration, that is, when the system is in temperature equilibrium with the reservoir, or equivalently, I can say where this is stationary with respect to U. U here is the energy of the system. So in other words, when du d sigma is equal to tau. And we saw that when the temperature changes and the volume changes, that the corresponding change in the Helmholtz free energy is minus sigma d tau minus p dv. And so that means, in particular, if we fix the temperature and consider isothermal changes, then the change in the free energy is the work done when the volume of the system changes. We talked about the partition function for a system in contact with a reservoir at temperature tau. We sum over the states of the system, e to the minus energy of the system divided by tau, the Boltzmann factor for that state of the system. The normalized probability for system in contact with reservoir of system state with energy E sub s is the Boltzmann factor. Dividing by the partition function makes it normalized, so that when we sum over states, the probability sum to 1. We said in the case of a large system, the free energy can be expressed as minus tau times the log of the partition function. And, well, in general, and whether the system is large or not, we can express the value of the energy averaged over this Boltzmann ensemble in terms of the partition function. Which I guess is tau squared du d tau. Pretty sure we did that. We can write the average energy as tau squared d d tau log c. That is, if we differentiate with respect to tau inside the summation, it brings down a factor of 1 over tau squared times the energy, weighting the Boltzmann factor. So that's the same thing as the mean value of the energy of the system in the Boltzmann ensemble. I think that's pretty much what we did last time. Any questions about that? Okay. So what we are going to talk about today is the ideal gas. We're going to make several passes at the ideal gas, each time with some new concepts and wrinkles added. Now, this is our first pass. We're going to consider a box. You might as well consider it to be a cubic box. It has side L. And there are going to be particles in the box which are non-interacting. They don't have any mutual potential energy. They only have kinetic energy. In fact, let's start out with just one particle. We're really interested in the case where there are many, but it'll be useful as a step towards analyzing the case where there are many particles to consider the case where there's just one. Consider one particle. It's one free particle. Only kinetic energy, not potential energy. That's what I mean by free. So the Hamiltonian is just p squared over 2m. As you know from 12b, regarded as an operator acting on a wave function, that's minus h bar squared gradient squared divided by 2m. We can find the energy eigenstates of the system by solving the Schrödinger equation, finding the eigenstates of that operator with appropriate boundary conditions. Now suppose we use the boundary condition that the wave function, a function of x, y, and z, it's a particle in a three-dimensional box, equals 0 at edges of box. And a problem that you previously solved is to find the energy eigenfunctions and eigenvalues. The eigenstates are labeled by three integers, so up to a normalization constant. I have sine pi nx x over L, where L is the side of the box, times sine pi and y over L, sine pi and z over L. That obeys the boundary condition when x, y, or z are equal to either 0 or L. The wave function vanishes. I can see it's an eigenstate when I take the derivative, it just brings down a factor of pi n x over L when I differentiate with respect to x. Similarly for y and z. The energy as a function of these three integers. When I of course have the h bar squared. Differentiate sign twice, I get a minus sign. Each time I differentiate, it brings down pi over L. The kinetic energy has a 1 over 2m. There's a pi over L squared. And then an x squared plus ny squared plus nz squared. Nx, ny, and nz are all non-negative integers. And they can't all be 0, since if they were all 0, the wave function would vanish. 1 or 2 can be 0. So, for our one particle in the box, is that clear? We can evaluate the partition function. I'll write z sub 1 just to remind us that we're talking about the case of one particle. So we sum over the integers, and x, n, y, and z. We can use those integers to label all the states. E to the minus epsilon over tau. Epsilon is this function of nx, ny, and nz. So just to substitute in and write out explicitly what it is, we're doing a sum of the exponential minus h bar squared divided by 2m. And let's remember I'm dividing by tau in the Boltzmann factor as well. I'll put the tau there. Pi over L squared times nx squared plus ny squared plus nz squared. That's C1. Now we're not going to evaluate this expression exactly, at least not for now. We're going to make an approximation. I'm going to call the thing that's multiplying an x squared plus ny squared plus nz squared, a dimensionless factor. I'll call it alpha. That's a dimensionless number, and let's suppose it's small. Okay? Well, one way of saying what it means when it's small is I've got a bunch of energy eigenvalues which depend on these integers. There's some spacing between them, but the temperature is large compared to the spacing. So the exponential, I guess I had one more parentheses, changes just a little bit when the integers advance by 1. So when we do the sum, we can approximate it pretty well by an integral. Think of it as like a Riemann approximation to an integral in the limit of alpha small. So in our leading approximation for alpha small, I can write z1 as an integral from 0 to infinity for each one of the three numbers, nx, ny, and z. Exponential minus alpha nx squared plus ny squared plus nz squared. Another way of saying what the approximation is, if I keep the temperature fixed, I can always just imagine the box gets really big. Alpha will go to 0 when L gets large with tau fixed. Okay, big box. So this is great because this is an integral I know it's a Gaussian integral. In fact, it's the same integral 3 times. Integral 0 to infinity. Let's write the integration variable as x e to the minus alpha x squared. For the nx integral, same thing for the ny integral and the nz integral, so it gets cubed. And this is just 1/2 of the result of integrating from minus infinity to infinity, e to the minus alpha x squared, because it's an integral of an even function. And we've done that integral before. It's the square root of pi over alpha. Okay, that's the thing that gets cubed. So, for the partition function for the single particle in the box, it's 1/2 square root of pi over alpha cubed. And this is alpha. So I can take out a factor of L cubed because I've now got a 1 over alpha, which goes like L squared, but it's getting raised to the 3/2 power, so that's L cubed, a factor of volume. And then what I have left is m tau over 2 pi h bar squared to the 3/2 L cubed. Right, because I had a 1 over alpha under the square root, and this is alpha. And then the square root got cubed, so m tau over 2 pi h bar squared. There was a pi squared here. Also, that became a 1 over pi squared because it's 1 over alpha, but then there's a pi in the numerator that cancels that. And I had and I combined the 2's together, so that's what I got. So I can define the quantity that's multiplying L cubed. I'll give it a name. I'll call it n sub cubed. And, of course, L cubed is the volume of the box. So I'll write that as V. So V is volume of box. C1 is a dimensionless quantity. And Q has the dimensions of 1 over volume. It's the same thing as the dimensions of concentration, number divided by volume. And so I'll call it the quantum concentration. And it deserves the name quantum because it's got an h bar in it. It's the thing with the dimensions of h bar that I can make out of the mass and the temperature. It's the thing that I can make which has the dimensions of concentration out of the mass and the temperature in h bar. It has a somewhat more direct physical interpretation than that. So it has the dimensions of 1 over length cubed. Well, I can say it's equal to some length to the minus 3. And now worrying about pi's and 2's for a minute, that length is h bar squared over m tau to the 1/2. And that gets cubed. And what's the interpretation of that length? Well, it's what we could call a thermal wavelength. So what I mean by that is if we think of the, there's a question here? what is the interpretation of what again? Z1. So Z1 is the partition function for a single particle. And I guess I've just erased this stuff, but we'll be able to use it to compute properties of the single particle in the box, like the free energy, from which we can get things like pressure and entropy. But really, I'm not so interested in a single particle in the box. I'm really more interested in n particles in the box. So I wrote Z sub 1 to remind you, so far just one particle. We'll consider more particles in a minute. So what I mean by thermal wavelength is we have a particle in the box, and if its kinetic energy is comparable to the temperature, its kinetic energy is h bar squared k squared over 2m, where k is the wave number. And that means that the wave number is something like m tau over h bar squared to the 1/2. And what I call LQ is essentially 1 over that wave number. So this is like the wave number, the de Broglie wave number, for a particle which has a kinetic energy comparable to the temperature. And its reciprocal is the corresponding wavelength. So this goes like lambda de Broglie inverse for a particle with kinetic energy comparable to the temperature tau. Okay. So the approximation we made, we can now come back and see really what it is. The approximation we made is that the concentration, is there a question? Oh. That 1 over the volume, the concentration is small compared to the quantum concentration. Or equivalently, that the box is big compared to the thermal de Broglie wavelength. So in some sense, the quantum effects, the fact that the particle behaves like a wave, should be a small effect because the box is much bigger than the wavelength. So we're kind of in a classical limit. Okay? I'll call that the classical regime. Box much larger than wavelength. Okay. But now we want to consider putting many particles in the box. So now consider n, large compared to 1, particles in box. And I want to compute the corresponding partition function for that case. Now I'm going to suppose that the particles are distinguishable, and then we'll come back and revisit this assumption later. So you can imagine that each particle carries a label. I've numbered them, 1, 2, 3, 4, and so on. So now I want to count the states. And there are a bunch of energy levels for a single particle in the box. Okay, particles are non-interacting. The Hamiltonian is the sum over I equals 1 to n maybe I should call it k equals 1 to n, of the momentum squared for particle k divided by 2m. So the kinetic energy is just additive. Each particle is put in an orbital. So I put particle 1 in one of the energy levels, and particle 2 has the same set of energy levels, and I put particle 2 in one of them, and so on. Particle 3 goes here. So I can specify a state, an eigenstate of the Hamiltonian for many particles, by specifying for each one of the n particles what orbital it's in. By orbital, I just mean a single particle eigenstate of the Hamiltonian. So each particle, we can say, occupies an orbital. A single, what I mean by orbital is a single particle energy eigenstate in the box. Now I want to sum over all states to compute the partition function. Summing over all states means for each particle, summing over all the possible orbitals it can be in. The energies just add up, right? Because the Hamiltonian is the sum of the kinetic energies of the particles. So for a particular state, I can write the total energy of the n particles as the energy of the first particle plus the energy of the second particle, and so on, up to the energy of the nth particle. So I've used labels here, I1, I2, In. So what I mean by I1 is that's the label for the orbital occupied by the first particle. And it has some corresponding energy, which I call E of I1. I2 labels the orbital for the second particle, and so on. And now I want to sum over all the states. So what does it mean to sum over all the states? Well, like I said, it means for each particle, summing over all the possible orbitals. So I sum the first particle over all the orbitals, which I'm labeling by an index I1. Sum the second particle over all the orbitals it could be in, and so on. I independently sum over the orbital occupied by particle k for k from 1 to n. So here, sum over orbitals for first particle, sum over orbitals for second, and so on. Okay? And that means I'm summing over all the possible states for n particles. So I want to evaluate the partition function. I'll call it z sub n, because it's the partition function for n particles. So that means summing over all the states of the Boltzmann factor, e to the minus e over tau. So e to the minus e over tau, well, e is this sum of the energies of each one of the particles. So that exponential of a sum can be factored into a product of exponentials. So e to the minus energy divided by tau, I can write as the product as the particle goes from particle 1 up to particle n, e to the minus the energy of the orbital occupied by particle k divided by tau. Now I want to sum that over states. But summing over states means summing over the orbital for the first particle, summing over the orbital for the second particle, and so on. So summing over all states, this product of exponentials is the same thing as taking the product of the sums for each one of the k particles over all the orbitals. So z sub n, I can write as the product from k equals 1 to n, and then sum over orbital occupied by particle k, e to the minus energy of that orbital divided by tau. Doesn't look much like a tau, though. Right? Because the sum over states, if you expand this out, in other words, this sum over I1, sum over I2, sum over I3 up to sum over In is the same thing as summing over all states. So the quantity in brackets here, that's actually the thing we already evaluated. That's the single particle partition function. For a single particle, this is the sum over all the orbitals times the Boltzmann factor for the orbital for a single particle. Okay? So in the end, the answer is very simple. It's just the product altogether n times of the single particle partition function. Okay? So I can write this as z1 raised to the power n, because this is actually just z1. Sum over all orbitals, e to the minus energy of the orbital divided by tau. The reason it worked is because the particles were non-interacting, so the energy was additive. Okay, the exponential of the energy, therefore factorized. And it worked because summing over all states meant summing over the orbital occupied by each one of the particles. And that was true because the particles were assumed to be distinguishable. Okay, I could talk about what orbital was occupied by particle 1, which orbital was occupied by particle 2, which one by particle 3, and so on. Now that we have the partition function, we can start using it to calculate other things of interest. Remember, we already computed what Z1 was. Here it is. Quantum concentration times volume. So the n particle partition function, which is Z1 to the n, is quantum concentration times volume raised to the n. Okay, and this is the quantum concentration. I guess I'll write that again. Quantum concentration equals mass of the particle times temperature divided by 2 pi h squared to the 3/2. So that's the n particle partition function. We said that if we wanted the ensemble average of the energy, we can write that as tau squared, derivative with respect to tau, natural log of Zn. We also said we could write the free energy. The Helmholtz free energy is minus tau times the log of Zn. Well, let's talk about the total energy, the average of the total energy averaged over this ensemble. Well, we're going to differentiate with respect to temperature. Where's the temperature dependence? It's in the quantum concentration. It has temperature to the 3/2, right? So when I take the log of Zn, which is equal to n times the log of quantum concentration times volume, the quantum concentration has a tau to the 3/2. So I can write that as 3/2 n times the log of tau plus something that's tau independent. Since all the temperature dependence came from that tau to the 3/2 in the quantum concentration. And so if I look at this formula, did I get a... that's true. Tau square. Okay, that's fine. Sorry. So then when I differentiate the log tau, I get a 1 over tau. Then I multiply by tau squared. So the ensemble average of the energy will become 3/2 n tau. Or if you want to write it in terms of the conventional temperature, it's 3/2 n, Boltzmann's constant, times temperature. Okay? So the average energy per particle is just equal to 3/2 kT. So for the free energy, I just have to take the log and multiply by minus tau. So that gives me minus n tau in front of natural log of quantum concentration times volume. Now remember, I guess I've erased it since writing it down to review Tuesday's lecture, that we know how to write changes in the free energy in terms of changes of volume and temperature. And that means I can differentiate the Helmholtz free energy to find pressure and entropy. The thermodynamic identity for the Helmholtz free energy. Yeah, question.
So if we get 3 over 2 at the bottom of the top 4.
Where did I get this 3 over 2? I got the 3 over 2 because the quantum concentration is temperature to the 3/2 times some factor which doesn't depend on temperature. When I take the log of the quantum concentration then, taking the log of tau to the 3/2 gives me 3/2 log tau plus something that doesn't depend on temperature. So since dF can be written as minus sigma d tau minus p dV, it means if I want to know the pressure for the case of the n-particle gas, I can differentiate with respect to volume with temperature fixed. If I want to know the entropy, I can differentiate with respect to temperature with volume fixed. And in each case, there's a minus sign as well. So let's do pressure first. So we want to differentiate this with respect to volume with temperature fixed. Temperature fixed means we're fixing the quantum concentration. The free energy for the n-particle ideal gas I can write as minus n tau times the log of volume plus something that's independent of volume. So when I differentiate with respect to volume and change the sign for the pressure, I get n tau, differentiating the log gives me 1 over v. So in other words, pressure times volume is equal to number of particles times temperature, or in terms of conventional temperature, and Boltzmann's constant times temperature, which is the ideal gas law. Okay. So that was nice. Let's figure out what the entropy is. So the entropy, again, is minus the derivative with respect to temperature of the free energy. Free energy is over here. So we're going to differentiate minus n tau times the log of quantum concentration times volume, and we're going to do that with volume fixed. And remember, the quantum concentration actually depends on the temperature. The quantum concentration is proportional to tau to the 3/2. So when we differentiate with respect to the temperature, there's temperature dependence in two places, the tau in front here, and the tau to the 3/2 inside the logarithm. So for the entropy, in the case of n particles, differentiating the first term gets rid of this tau, and then I have log times quantum concentration times volume. Differentiating the log of tau to the 3/2 gives me 3/2 over tau. That cancels the tau in front, the 1 over tau. And I have a 3/2 and two canceling minus signs. So I get, in addition, plus 3/2 the number of particles. Okay? So that's our formula for entropy. Now, this formula for entropy is quite interesting, and in a way, in several ways, a little bit mysterious. One thing that's interesting about it is it depends on h bar. When I calculated the ensemble average of the energy, I got a formula which would be recognized by a classical physicist and would have looked very familiar to Maxwell, for example. I said the energy per particle on average is just 3/2 kT, no h bars there. When I found our formula for the pressure, then we got PV equals nkt. No surprise to Boyle. No h bar there. But in the formula for the entropy, there's an h bar which hasn't disappeared because it's in the quantum concentration. Right? The quantum concentration has an h bar in it. If we think of h bar as a very small quantity, then the quantum concentration becomes big because it's going like 1 over the de Broglie wavelength, and that's getting very short. So as h bar goes to 0, which we normally think of as the limit of classical behavior, it blows up. It goes to infinity. Okay. Well, in a way that's kind of makes sense because for us the entropy was obtained by counting states. And if we want to count the states in the box at some fixed volume, some fixed size of the box, we only have a discrete set of eigenstates of the Hamiltonian, when h bar is non-zero, when we're doing quantum physics instead of classical physics. Now, in quantum physics, we really know how to count states because they're discrete in a finite box. In classical physics, it's a little harder to explain exactly what we mean by counting states. Okay, so we're doing quantum counting of states. And so h bar comes along for the ride to help us keep track of the number of states. Well, another thing that's interesting about the formula is this. So let me define n, small n, not capital N, as number of particles per volume, the concentration. So let me get rid of the volume, since I can now write it as the number of particles divided by the concentration, and write our entropy in terms of the concentration and the number of particles, little n and big N. Okay, so I'll replace volume in our formula by big N over little n. And then the entropy can be written as n times log of quantum concentration divided by concentration plus 3/2 n. But there's also a n now, a capital N, inside the logarithm. So I get an additional n log n term. Now, this is a pretty weird-looking formula because suppose I fix the concentration and I consider making the box bigger. So I'm increasing the number of particles. Okay? So normally we think of entropy, as I've said in a past lecture, as, and that's almost a question. You right? Yeah, what is it? Where does the log n come from? Yeah, the n log n came because I replaced the volume by n divided by concentration, since concentration is number of particles per volume. And then I wrote this as the sum of two logs, the log of nq over little n plus log n, multiplying an n in front. So if we keep concentration fixed and increase n, capital N, which means we're also increasing the volume and the number of particles together, this is not extensive. It doesn't scale linearly with the system size. Not quite, anyway. It increases like number of particles times log number of particles, not just linearly in system size. That's what I mean by not extensive. Now, there's a third interesting thing about the formula, which is it's wrong. And we made a mistake. We got the wrong answer. Where did we go wrong? Any ideas? What do I mean when it's wrong? Well, you can compare it to experiment. I'll come back later to how you do that. You have to consider adding heat at constant pressure. There are different ways of checking the formula. It doesn't work. It's wrong answer. It doesn't apply to an ideal gas. So we have to look back at our calculation and think how it could be wrong. Well, it's mathematically correct under the assumption stated. The assumption stated was the particles are distinguishable. So let's, just to make sure there's no confusion, call this the entropy for n distinguishable particles. I'll write disting because distinguishable is too many letters. To remind us that this is the formula for entropy that would apply if all n particles had labels and we could tell them all apart. Okay, I could say, there's Alice, Bob, Charlie, Denise. Every particle has its own name. So Gibbs mulled this over. Gibbs is another one of the heroes of statistical mechanics. And he made a brilliant and rather radical suggestion. He said, perhaps the disagreement with experiment is telling us it's wrong to think of the particles as being distinguishable. The particles are really indistinguishable. They don't have labels. You can't tell who's who. If so, we're not doing the counting of states right. So Gibbs said, suppose you got a bunch of orbitals. These are the orbitals. Now, I'll label them with letters, and I'll label the particles with numbers so we don't get confused about which label corresponds to which. So these are the orbitals. And the way we've been doing the counting so far, we've said, okay, I could take particle 1, and I could decide which orbital he's in. He's in orbital B. And I could take particle 2 and put him in orbital D. And I could, on the other hand, have reversed the roles of particles 1 and 2. I could have put particle 2 in orbital B and particle 1 in orbital D. The way we did the counting, these are two distinct states. Okay? So in both cases, there are two particles and two orbitals. The orbitals that are occupied are B and D. But the particles have labels, so I can tell the difference between particle 1 being in orbital B and particle 2 being in orbital D, as opposed to particle 1 being in orbital D and particle 2 being in orbital B. So distinguishable particles that would mean these are two distinct states. But Gibbs said it's wrong because the particles don't actually have labels. In both cases, there's a particle in orbital B and a particle in orbital D. And because we don't know who's who, those are just two ways of describing the same state. Okay? So indistinguishable particles these states are the same. Because I don't really know who's who. So we have to rethink the counting. And actually, we're going to come back. We'll be revisiting this several times to get the counting right. But first, let's notice that if we stick with the classical regime, the regime in which density is low, we can fix up the counting pretty easily. So we have an exercise to do. We need to fix our counting. And I'd like to consider the case of a low-density gas by which, in the case of a gas with many particles, I mean the concentration is small compared to the quantum concentration. So concentration divided by quantum concentration is small compared to 1. So if you want a physical picture, the particles really have de Broglie wavelengths, but this means that the separation between particles is large compared to the wavelength. The gas is dilute in that sense. And so they really behave like classical particles. The fact that the particles are really waves has only very small physical effects in this regime. That's why we call it the classical regime. So you can think about it this way, if you'd like. If we consider the case of a single particle, we ask what its entropy is. Well, it's the same formula we have for entropy except without the n, right? Because the entropy, well, that's essentially right anyway. So the entropy for a single particle in the box would go like log of the quantum concentration times the volume. Since we had n times the log of the quantum concentration times the volume, plus some additional term that we could take to be small compared to this term. So that means that the number of orbitals, essentially the number of states for a single particle, or the degeneracy, we could think of as being e to the entropy of the single particle. Well, I can take the exponential of the log and get quantum concentration times volume. And the regime I want to consider is the one in which this number of orbitals is large compared to the number of particles. So in other words, number of orbitals, the typical number of orbitals that a single particle will occupy, divided by the number of particles, is quantum concentration divided by concentration. And I want to consider that to be a large number, many more orbitals than particles. So what that means is we don't have to worry much about an orbital being occupied by two different particles. Okay? The configuration of the gas at a given temperature, there are many orbitals that can be occupied, but many fewer particles than orbitals, and so most of the orbitals are empty. A few have particles. Very rarely will there be two particles in the same orbital. Okay? So in this case, double occupancy by two or more particles, that is, two or more particles in the same orbital, is rare and can be neglected. So occupation a number of an orbital is either 0, which is true for most of the orbitals, or 1, not 2 or more. Okay? And that's a very good approximation in the limit of a very dilute gas, because there are many more orbitals than particles. So then it's easy to fix things up because lots of orbitals, just a few particles. So suppose there are n particles, n orbitals occupied. When we considered the particles to be distinguishable instead of indistinguishable, we overcounted by how much? We overcounted by a factor. That's the amount by which we were wrong. What is that factor? Each way of choosing n occupied orbitals was counted how many times? N factorial. Because we pretended in our initial counting that the particles had labels. Could have been 1, 2, and 3, or this could have been 2, and this could have been 3, and this could have been 1, etc. There are n factorial ways in which we can attach labels to the particles. So n factorial labelings of particles were all counted as distinct. But really, if the particles are indistinguishable, all describe the same state. So it's easy to fix things up. For distinguishable particles, I'll now write the n-particle partition function disting. That's the calculation we already did, and we saw in the quantum regime, the low-density regime, that's z1 to the n. If they're indistinguishable instead, all right, Zn indistinguishable, I have to include a correction factor, which is what? What should I include now? I summed over all the states before, as though all the particles were distinguishable. Now I want to sum over all the states, taking into account that they're indistinguishable. There are n particles. So the right counting differs from the initial way we counted by a factor, which is what? 1 over n factorial. That compensates for our overcounting. We counted each state n factorial times. So that's the right answer if the particles are indistinguishable in the quantum regime. So we're assuming, as we did actually in this calculation as well, that the gas is dilute, that n over nq is small compared to 1, what I'm calling the classical regime. All right, so now we can fix up our formulas. When we take the log of the partition function for n particles when they're indistinguishable, that's going to be the log of what we had before when we treated them as distinguishable. But now there's a correction, which is minus the log of the of n factorial. Under this assumption. So some of the predictions we made, which turned out to be correct ones, will be unaffected by that change. So, for example, when we computed the average value of the energy, by differentiating log z with respect to temperature and multiplying by tau squared, of course, we were doing that with the volume and the number of particles fixed. So that's unchanged. It's what we computed before, which is 3/2 n tau. So when we take the free energy, which is minus tau, times the log of Zn, and now we want to do that, well, in general, that's what it is. So that means when I write Fn for indistinguishable particles, it'll be the Fn we computed before for distinguishable particles. And then there will be a plus, because of this minus sign, it becomes a plus, tau log of n factorial. When we differentiate the free energy with respect to the volume, with tau fixed, well, that's again going to be unchanged. So we'll still have the ideal gas law, PV equals n tau. But when we calculate the entropy, something does change. Because the entropy for n particles was minus derivative with respect to temperature of free energy with volume fixed. And when we differentiate with respect to the temperature, we get that extra log of n factorial. So sigma, when the particles are indistinguishable, as indeed they are, can be written as the entropy that we would have had if they were really distinguishable, and then minus, because of this minus sign, after differentiating with respect to tau, log of n factorial. And we can use the Stirling approximation, as we're always inclined to do, writing the log of n factorial as n log n, minus n, plus order log n, which we'll neglect, as subleading when the number of particles is large. And look what happens. This becomes minus n log n plus n, plus other stuff we neglect. And that should be log n, natural log of n, and plus n, because there's a minus in front. And that gets rid of the offensive n log n. It also adds to the term linear in n, 3/2 n, another n, so it becomes 5/2 n. Well, I guess I'll erase that. so our new formula for the entropy of n particles when the particles are indistinguishable is n times the log of quantum concentration divided by concentration, and then 5/2 n. I'll put the 5/2 here, multiplying the n. Got rid of the n log n, change the 3/2 to a 5/2. Again, it applies in the classical regimes, assuming concentration divided by quantum concentration is small. And that is the right answer. And because it's right, it's named after people. Not that it's important to know. It's called the Secker-Tetrode equation. So sure enough, we fixed the problem. It's now extensive. The entropy scales linearly with n if we keep the concentration fixed. It still has the cool feature, though, that it's sensitive to h bar. Still true that the entropy blows up when h bar gets small. So it becomes infinite in the so-called classical limit when h bar goes away. So again, we got the answer now for a dilute gas, the so-called classical regime. Of course, we'll also want to do the counting right when the gas is dense, when the concentration is comparable to the quantum concentration. And we will do that, but not yet. We'll come back to that later. Well, it's an important question. What happens when the gas is dense? Talk about that later. So it's an interesting observation. The particles are really indistinguishable. And Gibbs thought that was interesting when you think about the following situation. So suppose you have a box. It's divided into 2 halves. And there's a wall in between. So there's gas in box 1 and box 2. And they're both at the same concentration. Same pressure, same density. And then we remove the wall. And so the gas from the 2 sides, initially separated, now mixes. So what happens to the entropy? Okay. Well, suppose we use our original wrong formula, the formula that would apply. So what happens to entropy when the 2 sides mix? Assuming particles are distinguishable. So let's use our formula that applies in the case of distinguishable particles. N log quantum concentration times volume plus 3/2 n. So we start out with N1 particles in box 1, which has volume V1, and N2 in box 2, which has volume V2. After we remove the partition, we have the total number of particles N equals N1 plus N2, and the total volume V, the sum of the volumes of the two boxes, V1 and V2. So how does the entropy change? I'll call that delta sigma. The entropy after we remove the partition and the gases mix up, that's going to be the total number of particles N1 plus N2 times the log of quantum concentration times total volume V1 plus V2 plus 3/2 N1 plus N2. And then I subtract away the sum of the entropies of the two boxes before we remove the partition. For the first box, that was N1 log quantum concentration times volume 1 minus 3/2 N1. And for the second box, minus N2 log quantum concentration times volume 2 minus 3/2 N2. So a lot of stuff cancels. Like this 3/2 N1 plus N2 cancels against this minus 3/2 N1 and this minus 3/2 N2. If I look at the terms that are proportional to the log of the quantum concentration, the log of NQ here times N1 plus N2 cancels against minus N1 log NQ minus N2 log NQ, so we don't have to worry about that. But there's still something left. The terms that go like N times log volume. N1 I have for delta sigma, the difference between the entropy after the partition is removed and the entropy before. It's N1 plus N2 times log of total volume minus N1 log of volume 1 minus N2 log of volume 2. Or I can write that as N1 times the log of the ratio of the final total volume divided by the initial volume of box 1 plus N2 times the log of the total volume divided by the volume of box 2. So in particular, just to be concrete, suppose that both boxes are identical. So if V1 is equal to V2, then both logs are log of 2. So I get N1 times log of 2 plus N2 times log of 2. So the change in the entropy is actually proportional to N. It's N natural log of 2. Okay? And so this is an irreversible process then. It increases the entropy. And once the entropy increases, we can't get the genie back in the bottle. We're in a more probable configuration than where we started. Well, actually, if you think about it, it kind of makes sense, because if you take the exponential of the change in the entropy, you get 2 to the n. Okay? So think of each particle. You have n particles. And initially, some of the particles have to be on side 1 of the box. Some of them have to be on side 2. Half of them are on side 1, half of them are on side 2. Now, each particle, after we remove the partition, has twice as many places to go. It can be either on box 1 or box 2. There's kind of one bit of information for each particle. And then once it decides to be on the left side of the box, there are many states it could be in. If it decides to be on the right side, there are many states it can be in. But each particle, after we remove the partition, has an additional choice, a binary choice, to be on either the left side or the right side, right? 2 possible choices for which side of the box for each of n particles. So there are 2 to the n more states. Okay? And actually, that would be the right answer. And this really would be an irreversible process. If, before I removed the partition, I had 2 different types of molecule on the left side and the right side. Okay? Suppose I had molecular oxygen on the left and I had molecular nitrogen on the right. Okay? And then we can tell these guys from these guys. The guys on the left are distinguishable from the guys on the right. Although all the oxygen molecules on the left are indistinguishable from one another, all the oxygen molecules on the other side are indistinguishable from one another. I mixed up oxygen and nitrogen. Anyway, you know what I mean. We remove the partition, and now the oxygen can be on either side. That's an irreversible process because after we remove the partition, we really do have a macroscopically different state where the oxygen and nitrogen are uniformly mixed. So if the genie really is out of the bottle, we can't reverse that and get spontaneously oxygen on one side and nitrogen on the other. Okay? And that's what that 2 to the n is telling us. But if I really have oxygen on one side and oxygen on the other side, then removing the partition doesn't do anything. I still have a box uniformly filled with oxygen. Well, macroscopically, it's really the same configuration. Nothing irreversible has occurred. Okay? And in fact, if we use the right formula for the entropy, taking into account that all the oxygen molecules are indistinguishable, as Gibbs conjectured, then there's no change in the entropy, right? Because it was the n log v term that caused the trouble, right? Or equivalently n log n. We got rid of the n log n. So if we consider sigma n indistinguishable, that formula up there, when we keep the concentration fixed, it's just n times a constant, proportional to n. And removing the entropy, yeah.
So when we were considering the magnetic spins, was that a distinguishable system or an indistinguishable system?
Well, we were considering the spins to be distinguishable. That's correct. Because, in fact, somebody asked the question at the time. In that case, it's a good question. We were asking a somewhat different question. We were not asking each spin, are you Alice, Bob, Charlie, or Denise? Okay? We were asking instead, for each spin, are you up or down? Okay? And it is a meaningful distinction to say that this spin is up and this one is down. But that doesn't mean that I know that this one is Alice and this one is Bob. Okay? So, or another way of saying it was, the spin made them distinguishable. I could distinguish spin up from spin down.
If they had all been indistinguishable, would all the states still have been equally likely?
Well, I mean, in a way, we treated them as indistinguishable in the following sense, that all the spin ups were considered to be indistinguishable. We didn't consider separate configurations where this is Alice pointing up and this is Bob pointing up, compared to when this is Bob pointing out and this is Alice pointing up. All we cared about is for each spin, is it up or down? So in a sense, we did treat them as indistinguishable. But there's they have what corresponds to what orbital they're in is spin up or spin down. Okay. So for each spin, I don't know. That we can we know which spin is at which position. Okay? And for each one of those, we can say whether it's up or down. And that's how we did the counting.
And each one of those counts as a different state.
Yes. It counts as a different state if we change the configuration, meaning for each one of these lattice sites in the magnet, we change which ones are up and which ones are down. But once we fix which ones are up and which ones are down, that completely specifies the configuration. So we don't try to distinguish between this spin being Irving and this spin being George. Okay, so that's the sense in which we're treating them as indistinguishable. All we care about is whether they're up or down. Okay, so the last remark I was going to make is that if we use our formula for indistinguishable spins, then the entropy just scales like n. So after we remove the partition, it's proportional to n1 plus n2. Before we remove the partition, it was proportional to n1 for the first box plus n2 for the second. There's no change. So in that case, delta sigma is equal to 0. If we have oxygen on both sides, there isn't some irreversible process that's occurred. Okay. So as we proceed in the next couple of weeks, we'll be returning several times to this issue of distinguishable versus indistinguishable particles and seeing how to do the counting right when particles are indistinguishable. But beyond the classical regime that we talked about today, so far we've just reproduced what you knew about classical ideal gases. It'll be more exciting when we explore the properties of quantum ideal gases, where quantum effects really are important. And we can't necessarily treat the de Broglie wavelength as a very tiny length that we can neglect. Okay.